Hello everyone, I hope you are doing well. I am talking about our project which is detecting financial fraud with machine learning, and our team members are Furkan, Emre, Ginyol, Emirhan Hosanlı, Melih Çifçi, Qadeer Osmani, and also Seif Elredeini. Our financial fraud detection app uses machine learning models such as SVM and also random forest in order to analyze transactions and detect fraud in real time. It also delivers instant and accurate classification with a user-friendly interface, which this helps businesses reduce risks, improve efficiency, and also strengthen the customer trust. Fraudulent financial transactions cause major losses and erode trust. At the same time, traditional methods fail to keep up with evolving with the fraud. This project that we prepared applies machine learning, including SVM and random forest, to analyze data, detect anomalies, and also build accurate, scalable fraud detection models. By improving real-time detection and also balancing precision and recall, we aim to reduce financial risk and enhance institutional trusts. Financial fraud is a rare but highly impactful, with class imbalance posing a major challenge. So traditional systems often struggle with false positives and false negatives, leading to inefficiency and undetected fraud. Our goal is to develop a real-time fraud detection system that balances precision and recall and also minimize losses and ensure robust detection. Detecting fraud requires tackling class imbalances and adapting to evolving techniques. Anonymized data complicates model transparency, and real-time detecting demands fast and accurate system. So we address these challenges with feature engineering, resampling, and also in-sample modeling to create efficient fraud detection system. Why it is important to have the fraud detection system? As you may know, fraud detection system mitigate risks and protect institutions and customers. Using techniques like SVM, random forest, and smoother, we address class imbalance and improve accuracy. Advanced pre-processing, including feature engineering and PCA, ensures that the system adapts to evolving fraud patterns while maintaining precision and recall. Machine learning also analyzes large datasets to detect fraud. Algorithms like SVM and random forest addresses rare fraud causes effectively. So techniques like smoother feature engineering and a high parameter tuning improve precision, recall, and adaptability, which make these models essential for robust fraud detection. Our training dataset includes 284,807 transactions, with only 492 labeled as fraudulent, featuring anonymized variables like V1 and V28. A Kaggle source testing dataset validate performance on new patterns. Key challenges include class imbalance and also handling anonymized features. Pre-processing step including missing values handling, scaling with standard scaler, and also balance with smoother. Metrics like precision, recall, and ROC, AUC ensures reliability in this part. Pre-processing involves handling missing data, cleaning duplicate, normalizing transactions amount, and addressing class imbalance using smoother. These steps ensures data quality and balance, improving model performances. We normalized transaction amounts with a standard scaler, reduced dimensionality using PCA, and also performed correlation analysis to focus on key fraud indicators like transaction amount and frequency. These steps improved accuracy and detection efficiency in our project. We used SVM, which is ideal for high dimensional and nonlinear data, and random forest, a robust, scalable ensemble method that reduces overfitting and handles imbalanced data effectively. Together, these models provide accurate and reliable fraud detection within our work.
Model training and testing. The dataset was divided into training 75% and testing 25% subsets using stratified sampling to maintain class distribution and ensure reliable evaluation. We applied cross-validation, including grid search CV, to fine-tune hyperparameters and validate model performance. This process ensures the model is robust, accurate, and generalizes well to unseen data. Model evaluation metrics. To evaluate the performance of our models, we focus on three key metrics. Accuracy. This measures how often the model's predictions are correct overall. It provides a general sense of the model's performance. Precision. Precision tells us how many of the flagged transactions are actually fraudulent. It's crucial to minimize false alarms. Receiver operating characteristics and area under the curve. This metric evaluates the mobile's ability to differentiate between fraud and non-fraud cases. A higher area under the curve means better distinction. These metrics are chosen to ensure the model achieves a balance between accuracy, precision, and reliability, which is essential for real-world fraud detection. Results and comparison. We evaluated the models based on accuracy and recall, with random forest achieving higher recall for detecting fraudulent transactions. Algorithm suitability shows that random forest is more robust for imbalanced data, while SVM effective handles high-dimensional features. Additionally, applying smooth improved detection of rare fraud cases by balancing the dataset during training.
Model validation. The confusion matrix revealed that random forest performed better in detecting fraud with less false negatives compared to SVM. However, SVM excelled in classifying legitimate transactions but struggled with false negatives due to the imbalanced dataset. The ROC curve showed that random forest and SVM balanced true positive and false positive rates effectively, with random forest demonstrating slightly better overall performance. ROC curve analysis. The ROC curve illustrates the trade-off between sensitivity and false positive rates across thresholds. For SVM, the AUC score is 0.97, indicating high reliability in distinguishing normal and fraudulent transactions. Its curve approached the top left corner, showing effectiveness despite class imbalance. For random forest, the AUC score is 0.99, demonstrating near perfect discrimination capabilities and highlighting its robustness in detecting rare fraudulent patterns. Confusion matrix overview. The confusion matrix provides a detailed breakdown of predictions, highlighting true positives, true negatives, false positives, and false negatives. For random forest, it accurately detected 17,055 normal transactions and 23 fraudulent cases, with only 6 fraud cases missed and 5 flagged incorrectly. This demonstrates superior precision and recall compared to SVM. For SVM, it identified 17,558 normal transactions and 4 fraudulent cases, but misclassified 25 fraud cases as normal and 2 normal cases as fraudulent. This highlights the need for further optimization to reduce false negatives. For the implementation plan, our system ensures real-time fraud detection, processing large transaction volumes with minimal latency. It incorporates pre-processing pipelines for normalization, feature transformation, and balancing, along with optimized models like random forest and SVM deployed on scalable platforms. It delivers quick, accurate results with monitoring dashboards to track performance. Model retraining keeps the system effective by regularly updating models with fresh, real-world data. This updates the system to evolving fraud patterns, fine-tunes parameters, and reduce false positives while maintaining accuracy. Scaling: The standard scaler is a pre-processing tool that standardizes features by removing the mean and scaling to unit variance. This ensures all features contribute equally to the model's performance, preventing larger value from dominating results. It is particularly useful for algorithms sensitive to scaling, such as SVM and PCA, ensuring consistent and reliable model performance.
Introduction to the system. The experiments demonstrated how pre-processing and feature engineering improved model performance. The random forest model achieved higher recall, while S7 handled high-dimensional data effectively. Refinements and Introduction to the system. The experiment demonstrated how pre-processing and feature engineering improved model performance. The random forest model achieved high recall, while S7 handled high-dimensional data effectively. Refinements enhanced the system's ability to process large transaction volumes efficiently and accurately, laying a strong foundation for real-world deployment. The GUI built using Streamlit integrates a pre-trained random forest model loaded via joblib. Users can input transaction details, including features v1 to v28 and the transaction amount, which are processed into Pandas data frame. The system classifies transaction as either fraud or normal transaction. Key features: the design is modular and scalable, with error handling to ensure robust functionality. This makes the application user-friendly and efficient for real-time fraud detection.
Hello everyone, today I am excited to present the notebooks from our fraud detection machine learning project. Our project is structured to showcase the necessary steps in a typical machine learning pipeline. It begins with data exploration and pre-processing, where we analyze and clean the data to ensure quality. We handle missing values and fill them with mean or median or drop rows. We do data cleaning by removing duplicates or normalizing or scaling numerical features. And then we use exploratory data analysis to analyze dataset structure. And we see our correlation analysis. Then we dive into feature engineering and selection. It's a critical phase where we identify the key attributes that will enhance our model's performance. For big data, we work with chunks to get a better performance. Here we initialize our models. We use smooth for handling class imbalance. We scale some features like amount. And we train our model. Here we experimented with multiple machine learning algorithms, comparing their effectiveness using metrics such as accuracy, precision, recall. Here we visualize our confusion matrix for SVM and random forest. And we see our ROC curve for our SVM and random forest. Here we use hyperparameter tuning to find best parameters. In order to do that, we use grid search CV. Here we see our best parameters, and we learn that random forest works better. Again, we visualize our confusion matrix and ROC curves. After this, we create the GUI for both desktop and in order to use in web. Let's make a test. Here I entered some values from our dataset. I make a prediction and it's fraud. Throughout the project, we emphasized interoperability and scalability, ensuring the results can be understood and applied in real-world scenarios. These notebooks encapsulate both the technical and analytical efforts that went into building a robust fraud detection system.